Speyer's G conjecture.
All right. Thanks, everyone. Yes. So this is work being written up with Andy Burgett, hopefully to be finished in a couple months, but you know what it means when a person says that. So this is, I will start with the perspective of Matroids as polytope, which thankfully both Graham and Jose introduced yesterday. So maybe by the third time, if you haven't seen this, it won't look too intimidating. So we can encode matroids as 0, 1 polytopes by taking the convex hull of the 0, 1 indicator vectors of their bases. And then you recognize if you had a matroid, because all of the edges are just exchanges. Subtract 1 from one coordinate, add 1 to one coordinate. And so you can see, if you had a matroid or if you have a bad edge like that, that's not a matroid because the exchange property is violated there. So these are matroid polytopes. And, forward. Let's try forward. Graham also introduced this idea of valuations. So, given the other definition of the relation that he gave, although he mentioned it, if I have a matroid polytope, like this octahedron that corresponds to U24 at the bottom, I can imagine cutting it up into smaller matroid polytopes. A way of doing that is called a matroid subdivision, like cutting this octahedron in half into the 2 square pyramids, each of which corresponds to U24 with the basis removed. And then we're interested in functions which have an exclusion-exclusion type additivity anytime you have such a relation, and these are what we call valuations. So, okay, it's written out formally here. If M is the big matroid and M1 through Mk are the maximal matroids that are faces, in this case K is 2, there's the top and bottom square pyramid, and you take all intersections, add them with a sign, which gives you the inclusion-exclusion, then you should get the big matroid. So in this case, I get plus 1 of these, plus 1 of these. I've double counted the square in the middle. I should subtract that off, and I should get the whole octahedron that way. A function which does that is called a valuation. Graham invoked but didn't define the notion of co-valuation, and that's just the sign twist of this thing. If I want the function just to add with no signs, well, I just, tailor the definition to get rid of the sign. Okay, let's just erase it. Go away sign. There we go, okay. Now I just, want to all the signs to be positive. If you like, I'm thinking of the interiors of all of these pieces. The interior of the octahedron is just the union of the interiors of these 3 polyhedra with no funny business about overlaps. So a co-valuation is just something that has a similar relation in every subdivision, but I've twisted the sign so I don't have to see signs in this relation. Okay. Speyer's G invariant was in my title, to be distinguished from Dirkson's G. Dirkson's capital MathCal G. This is just Speyer's lowercase ordinary G. So what's Speyer's lowercase g? It was introduced by Speyer in an attempt to answer an extremal question. If I have a matroid subdivision, maybe it's of the uniform matroid, because that's the matroid with the most bases, with the biggest polytope, fixing the rank and ground set. How many cells can I cut it into? How many cells of each dimension d could you have in such a subdivision? Natural extremal question on these matroid subdivisions. So, well, you can ask this. Let's say first I ask it for the maximal dimensional cells. This is an n-1 dimensional polytope, as we saw yesterday, because the coordinate sum is always r. That's one linear condition, so it lives in the space with one linear condition. So d is n-1, that's the biggest it can be. And how many n-1 cells you can have in such a matroid subdivision, it turns out, is answered by Crapo's beta invariant. So I have a theorem here which is due to Crapo except for the single word co-valuation, or valuation, which is due to Speyer. Otherwise, this is just theorems of Crapo. What does the beta invariant do? Well, this is a natural number valued function of matroids that is strictly positive if and only if the matroid is connected. And it turns out that a matroid is connected if and only if its matroid polytope is full dimensional. If it's not full dimensional, then you have some partition into connected components, and each connected component gives you one of these linear equations. So in fact, each connected component makes the dimension drop by 1. So connected means dimension as big as it can be, and the beta invariant recognizes this. It's positive for full dimensional, that is connected matroids, and 0 otherwise. And it's a co-valuation. It's actually both a valuation and a co-valuation, because it's 0 on low-dimensional things, so whether you add or subtract 0 doesn't matter. But it's a co-valuation. So this means if I have a subdivision, I add up the betas of all the pieces, I get the beta of the whole thing. Well, each beta is non-negative. Beta of the whole thing, if the whole thing is my uniform, is this binomial coefficient. So that's the largest number of actually positive summands I can possibly see. Every full dimensional piece gives you an actually positive contribution, so this is the largest number of full dimensional pieces I can possibly see. So that's an upper bound for D is n minus 1, and it's tight. Turns out it's tight. Beta equals 1 is attained by series parallel, and you can always, in fact, chop the uniform matroid into series parallel matroids. So Crapo's beta invariant answers this question for top dimensional pieces, and the raison d'etre of Speyer's G invariant is to try to answer this for all the dimensions of faces. Well, we'll look at interior faces, because it's the interior faces which come up in the equation for valuations and co-valuations. You just add over the interior faces because of inclusion-exclusion. If you want faces on the boundary, you can do the combinatorics yourself and figure out those extremal numbers. We'll look at extremal faces. So we'll make a generating function by dimension and have a univariate polynomial valued invariant, so that the dimension tells you the degree of the thing. The exponent of t tells you the dimension of the face. Actually, I'll index it the other way, kind of from the bottom. So t to the n is going to correspond to matroid polytopes of codimension n, which, remember, that is n connected components. So the degree n term of this thing is going to correspond to how many connected components the matroid has, and there can be higher degree correction terms to make the thing add up correctly. So if you had a polynomial valued co-valuation like this, which was positive in the term it needs to be positive and non-negative everywhere, then you could run the argument I gave in the previous slide in all dimensions at once, right? You could say sum up this G for every internal cell in the subdivision, and the sum equals G of your whole thing, G of your uniform matroid, and so the coefficients of G of your uniform matroid bound the number of cells of every dimension. That was Speyer's plan for an attack on this problem. And it works as long as the thing has non-negative coefficients. I will give you a definition. I'm postponing the definition. But Speyer was able to define something which you could show had integer coefficients. Using some characteristic zero algebraic geometry, he could show it had positive or non-negative coefficients in the characteristic zero representable case, but couldn't do it in general. And so that was the conjecture that he made in this 2009 paper, that this function g, which I'll define shortly, had non-negative coefficients, and then using that you could run this extremal counting argument. So this is the thing that my forthcoming work with Andy Birgit does. It's actually in two pieces. This is the piece I'll say nothing about for time, but we prove it in 2 steps. First, we reduce it to just showing that the top coefficient, the one with highest degree, is positive. Turns out that implies the rest of the coefficients are positive. This is something we did in 2016, but are lazy and haven't written up. And then with Andy Birgit, we have proved that this top coefficient is positive, which implies all the coefficients are positive, which proves this theorem, will prove that this theorem of Speyer can be used to do this extremal computation. If you're interested in the extremal numbers you get out of it, it's this trinomial coefficient. So that trinomial coefficient is the maximal number of interior faces of any matroid subdivision, and it's achieved by the same subdivision of the uniform into series parallel pieces. Okay. So that's the theorem. Now how about the definition? Okay. Well, I lied. Okay, okay, I'll say the definition. For those of you who like the algebrogeometric stuff, in a sentence, Graham mentioned the tautological bundles of matroids. What you do is you take exterior powers of the tautological bundles of your matroid, tensor them together, take the Euler characteristic, and those are the coefficients of G. But okay, this is not an algebraic geometry conference, so let's characterize G combinatorially. It's not so clear that this defines a well-defined function, but it turns out it does. Speyer checked that this agrees with the algebrogeometric thing I just said, and you can actually, if you're happy with these polytope subdivisions and producing polytope subdivisions, you can usually use this to evaluate G at least. So this is functionally sort of a combinatorial definition of G. Matroids with loops and co-loops I'll ignore because they will always lie on the boundary of the polytope. So the smallest matroid without loops and co-loops is U12. That'll be my base case. G of that thing is T. If you make series and parallel extensions, this G doesn't change. So in fact, G of any series parallel matroid is just T. It's multiplicative under direct sums, and it is a co-valuation. That is maybe that should go in the proposition too. But these four things together mean that when you can cut a matroid up into series parallel pieces, or add things, take things away to relate it to series parallel pieces, then you can use this to evaluate G. So for instance, to evaluate G on U24, you cut it into two copies of the square pyramid. Well, the square pyramid is this guy. It's series parallel. So each of those contributes a T. The square is U12 plus U12, so it contributes a T squared. So the whole thing is 2T plus T squared. Right? Indeed, it's just the face enumerator of this thing. I've got two three-dimensional faces and one two-dimensional face. 2, 1. So that is what the G invariant is if you're fluent with building these polyhedral subdivisions. Okay. So, yes, question. I need to prove it's well-defined. For instance, you can use the result that Graham mentioned of mine with Dirksen that characterizes the valuations in terms of Schubert matroids, and you show that, this gives you, you show it's well-defined for Schubert matroids, and then you can extend it valuatively. Yeah. So that's what I did. All right. So I want to show here a little bit of the algebraic geometry, but mostly the combinatorics that underlies this. And sort of the surprise, when Andy and I started digging into what was, the combinatorics that the proof dug up for us, everything I've done so far just has one matroid, but there is a very natural way to actually put two matroids on the same ground set as parameters into here, so that if you take them to be equal, then you get this top coefficient of Speyer's G, and in fact, you can get the rest of the coefficients as well. And if you take them to be unequal, you get some interesting stuff. And so I want to tell you what you get in the general setting. There's some nice matroids that come up. And I'll sort of say in one slide how the proof goes, and then focus on the nice combinatorial bits of the proof. So in one slide, how does the proof go? Well, we separate the case of realizable over the complex numbers, and then the general case. Realizable over the complex numbers, we use algebraic geometry. The general case, we do some more combinatorial stuff. So the algebraic geometry, okay, what does it do? Well, there is this tool, Weymann's geometric method for syzygies, that says, oh, if I have exterior powers of line bundles, I can relate that to free resolution of a variety you can construct using this recipe Weymann gives you. And the variety is the thing that, per Graham, I guess we should call the diagonal Dilworth variety. It's a reasonably hands-on thing. If I have two representable matroids over C, so I have two linear subspaces of C to the n, that represent my two matroids on n, what do? I take a vector from the first, a vector from the second, stick them together in a 2 by n matrix, and then rescale the columns. And the set of all matrices I get that way, okay, I close it, it's a risky close it, so I get a variety. But the set of all matrices I get that way, this is the tool that Weymann hands us, called the diagonal Dilworth variety. And its free resolution encodes the numbers we want, and some commutative algebraic magic happens here. You can take the initial ideal of this thing. That doesn't change the shape of the free resolution. That is magical. And so you can get monomial, square-free monomial ideal, which is initial ideal of this thing, which also has the same free resolution. So we can do this stuff. But once we have a square-free monomial ideal, Stanley Reisner says that's the same thing as a simplicial complex. So now we're back to combinatorics. We can just associate a simplicial complex to this variety that encodes the thing we want, and now a simplicial complex is something we have the chance of making for matroids if we're not given a representation. So in the non-representable case, that's what we do. We make the corresponding simplicial complex with a generalization of external activity for this diagonal Dilworth truncation, and then using the fact that representable matroids generate all matroids up to valuation, we can take the agreement from the realizable case and convey it to this case as well. So yeah, it's these things I want to tell you about. And I'll start by saying a hint about why we generalized it to two matroids, in that this way it also encompasses usual activity in the way that Ardilla and Booker found when they were looking at the Matroid-Schubert variety. So I suppose in this room we all know about fundamental circuits and activity. So here's the definition of what it means for an element that's not in a basis to be externally active. It means it's the smallest element in the fundamental circuit. And I want you to think of that as, like, I'm going to two-color every circuit, but I'm just doing it so that the minimum element gets one color and all the others get the other color. And that two-coloring is how I'm going to think about external activity. The sort of main combinatorial result of Ardilla-Booker about external activity is then a duality between bases and circuits with this coloring. What kind of duality? Well, if I have a simplicial complex, I can describe it in two ways, by the largest things in it, the faces, or the smallest things not in it. If I just have the independence complex, the largest things in it are bases, the smallest things not in it are circuits, right? So bases and circuits are dual in this way. And you can enrich this with the external activity coloring to give a corresponding duality between colored bases and colored circuits. So the external activity complex that these two build expresses this duality between colored bases and colored circuits. If I take each circuit of a matroid and just color its minimum element with the color X and all the other elements with the color Y, and I say these are going to be the smallest sets, the smallest faces not in my simplicial complex, then what are the biggest faces actually in my simplicial complex? Well, these are colored circuits. You'd hope for colored bases. Indeed, they are colored bases. How do we color the bases? Elements in the basis, you give both colors. Elements not in the basis, you color according to whether they're externally active or not. So this definition plus theorem, you define this complex one way and it satisfies both of these presentations. This is sort of the combinatorial heart of the work that introduced the Matroid-Schubert variety. And then there was also algebra and geometry in that work, which was, if you build the Matroid-Schubert variety, what do? You take your linear space, projectivize each coordinate separately, embed it in this product of P1s. Well, okay. Now if I want to take the ideal of that, I should move it back to affine space. So I move it back to affine space, and each P1 has two coordinates, two projective coordinates, so those are one of the columns of my matrix. So I get 2 by n matrices. You take a point from your linear space, you put all 1s at the bottom, and then you scale each column. So this is a case of the diagonal Dilworth variety, where my first linear space was the given linear space, and my second linear space was just the line through the all 1s vector. Matroid-Schubert varieties are a case of diagonal Dilworth varieties. And the way they hooked the algebra to the combinatorics was by showing that an initial ideal of this thing gives you the Stanley-Reisner ideal of the simplicial complex I just showed you that expresses external activity. Then you can do nice enumerative things. For instance, you can find the no broken circuit complex as a link of all the x's face in here, so you can count no broken circuit sets and relate it to the Tut polynomial, et cetera, et cetera. There's a lot they do in this paper, but this is what I think is the key. Right. So, as I printed it here, this was one arbitrary linear space and this special line. But this is the thing. It turns out you can do perfectly well for any two linear spaces. What matroid do you get out of this? If I start with two linear spaces, then, well, maybe I should show you the last thing on this set of let me show you this. Okay, so I start with two linear spaces, two represented matroids. Dilworth was interested in the problem of, taking a geometric lattice, removing the atoms, and turning the rest back into a geometric lattice so that the new atoms were rank 2 things, spans of 2 points in the original. And so the diagonal Dilworth truncation is a case of this, sort of represented by the bottom construction. If I've got a representation of my two matroids M1 and M2, I take the direct sum of the two representations. For each vector, I take the line in this projective drawing, the plane, spanned by the vectors in one representation or the other. So now I have a plane for each element. I want to get back down to a line for each element. So I intersect with the generic hyperplane. And this lets me transform representations of my two input matroids into representation of a new matroid. And this thing we call the diagonal Dilworth truncation because it's doing Dilworth truncation and then restricting to the diagonal, restricting to the pairs of points of the same color. So in the representable case, that's how you do it. Okay, we write down a bunch of characterizations. This is, if you like Edmonds, you can parse this definition, but you have a very nice description of its independent sets. Its independent sets, it's almost the matroid union, right? Its independent sets are all sets which, if you add an element, repeated or not, you can always partition that into independent sets in each. Its circuits are the minimal things where the sum of the two ranks is the size of the circuit. Lovely descriptions there. We'd like to have a nice description of the flat so we could do Bergman fans. We don't know one. White asked if there's a good one. I'd love it if anyone knows one. So we can describe some parts of this matroid, or some cryptomorphic descriptions of this matroid reasonably well. And then, in particular, we get a generalization of the thing Ardell and Booker were doing, that if we put one of the matroids in as U1n, and then we do this construction, we just get the other matroid back again. So it really is a generalization. Normally, or in generic cases, the rank is the sum of the ranks minus 1. It can be less, just like in matroid unions. The rank is normally the sum, but it can be less. This is like rank 1 less than the matroid union. That's not a theorem, but it behaves roughly like it. Okay. So, using this, we can give this generalization of activity as follows. So, external activity, I wanted you to think of it as a coloring of the circuits, but I only used the X color once in every circuit. And now I want to change that. Now I want the independent structure in my two input matroids to govern how I use the colors. So the characterization of the circuits of this matroid D I just gave says that any circuit of D can be partitioned into independent sets, into bases for C in each of the two input matroids. So there's lots of ways to do that. And I'll pick the initial one of those. I'll use some weight for each element, and I'll choose the largest weight way to partition it. And I'll do that for every circuit. I fix the weights of each X. I fix the weights of each Y. For each circuit, take the largest weight way to partition that circuit of D, color it accordingly. And those colored circuits are what we want to think of as the generalization of activity for two matroids. And the first sign that this is a sensibly behaved notion is that you still have the duality between colored circuits and colored bases. The simplicial complex, whose minimal non-faces are the colored circuits, has colored bases as its maximal faces, where now we call this coloring the generalization of basis activity, except it's not in or out so much, it's just like, is it M1 or M2 it belongs to, like the X colors or the Y colors, so we just called them 1 active or 2 active. And unsurprisingly, the algebra, or the commutative algebra also tells us that when you take this initial ideal of the diagonal Dilworth variety, you get this external activity complex of the diagonal Dilworth truncation. They're the circuits and bases of the diagonal Dilworth truncation, but colored in the way that remembers what your 2 input matroids were. So that's the generalization of activity we made. So I'm basically out of time. I guess I'll just say, I would love to understand this matroid and this coloring better. We have, one tool which we can show some things with, which is tropical intersection theory. But, we'd love to understand how this notion of activity, for instance, interacts with usual internal activity. This is like generalized external activity. And it looks like if we could combine that with internal activity, we would have an enumerative interpretation for G. But we don't have that yet. I would love your ideas. I'll stop here. Thank you.
We'll save questions for Alex for the break.
Sure.
Unless anyone has a very quick one. No, good. Perfect.